Hello Nathanga, welcome to GullyClassroom. This is the fourth lecture in the chapter Atoms in CBSE 12th Standard Physics chapter 12 Atoms or Atomic Structure. This is the fourth lecture taken in English. This is the fourth lecture of chapter Atoms taken in English. Sir, what are we going to learn in this particular lecture? We are going to learn how to derive the radius of the nth orbit with respect to Bohr's atomic model. The radius of the nth orbit with respect to Bohr's atomic model, and also we will learn the derivation of velocity of the electron in the orbital. Velocity of the electron in the orbital. We will do some 4 to 5 problems based on these derivations. All these problems are exact board problems, so I will recommend sincerely that you study these problems. Okay, before we go for this derivation, let us do a very short recollection of what we have learned so far. We studied about Bohr's atomic model. We studied about Rutherford's atomic model. With respect to Rutherford's atomic model, the very great limitation is the electron, as it goes around the nucleus, is an accelerated charged particle, and an accelerated charged particle, according to Maxwell, radiates energy. So the electron will spiral and fall into the nucleus. Hence, the atom is unstable. This is one of the major disadvantages of Rutherford's atomic model, but Bohr gave a suggestion that the electron, while going around the nucleus, is doing so in very specific orbits which are called as stationary orbits. These stationary orbits are defined with respect to angular momentum, and when these electrons are going around the stationary orbits, it is not losing any energy. Sir, on what basis did Bohr do this assumption? Bohr did this assumption based on Balmer's assumptions, Balmer's mathematical ideas. This was already discussed in the last lecture. Bohr did this assumption based on Balmer's mathematical ideas. It was already discussed in the last lecture. Can we go for this derivation? Yeah, come on, Kana. So, Bohr's derivation, Bohr's derivation or Bohr's radius. Anyway, this entire thing, Bohr's entire mathematical derivation is applicable only for single electron species. Applicable only for single electron species. Okay, give me 1 second. I forgot to put the cloth. I forgot this. I mean, to rub the board, I need the cloth, right? Sorry for the interruption. So, Bohr's radius. So, Bohr's radius, the entire idea of Bohr, the derivation of Bohr's radius and Bohr's velocity is only applicable for single electron species. Sir, what is single electron species? Let us take hydrogen. Hydrogen atomic number Z is equal to 1. Hence, it has only one electron. So, hydrogen can be called as a single electron species. What about helium? Sir, for helium atomic number is 2, but it has 2 electrons. If I put a plus here, helium has lost 1 electron. So, helium can be considered as a single electron species. What about lithium? Atomic number is 3. So, it must have 3 electrons. I am going to put 2 pluses here, which means it is losing 2 electrons. 3 minus 2 is 1. So, once more Li++ is a single electron species. What about beryllium? Z equal to 4. So, atomic number is 4. It has 4 electrons. It is going to lose 3 electrons. This is a single electron species. What about boron? Atomic number Z is equal to 5. Here, boron is going to lose 1, 2, 3 and 4. 4 electrons. Hence, it can be called as a single electron species. In a similar way, I can define any number of single electron species and the Bohr's derivation for the radius of the nth orbital can only be applied. The Bohr's derivation for the radius of the nth orbital can only be applied for a single electron species. Let us say here there is a nucleus, a positively charged nucleus. Here there is an electron which is simply going around the nucleus. The radius of the nth orbital means this particular distance. Are you able to understand the radius of the nth orbital? Okay, sir. So this is the radius of the nth orbital. Now, let me write R over here. Let me write R over here. This particular positively charged nucleus is attracting the electron with the electrostatic force of attraction. So, the nucleus is attracting the electron with the electrostatic force of attraction. This electrostatic force of attraction between the nucleus and the electron is providing the necessary centripetal force. Necessary centripetal force for the moving of the electron around the nucleus. For the electron to go around, to revolve around the nucleus, it needs a centripetal force, and the centripetal force is provided by the Coulomb's force or electrostatic force of attraction between the nucleus and the electron. So let us equate this. We are going to equate both of them. So electrostatic force of attraction can be written as, okay, let me first start by writing rather than mv square. Okay, electrostatic force of attraction can be written as 1 by 4 pi epsilon naught, where 1 by 4 pi epsilon naught is a constant q1 q2 divided by r square. q1 and q2 represent the charges of the nucleus and the electron. R square is the distance between them. This is nothing but equal to centripetal force. The formula for centripetal force is mv square by r. We have already learned this in +1. Okay, let us continue this particular derivation. Okay, here what is q1? q1 is the charge of the nucleus. So the charge of the nucleus is z into E. What is Z? Z is the atomic number, gives the total number of protons in the nucleus. E is the charge of the proton. And we are also going to take E has the charge of the electron. E has the charge of the electron. When we are substituting in Coulomb's force, when we are calculating Coulomb's force or substituting value of charge in this particular value of electron's charge in Q2, you need not add the symbols. You need not add the symbols, which means I can simply put E and not minus E. I will simply put E and not minus E. Let me write R square over here, and here I am going to go for mv square divided by R. Okay, let me cancel this and write. I can cancel this and write simply R. What is the next step? Next step is 1 by 4 pi epsilon naught. Let me write it like this. I am going to bring this particular mv square over here, and I am going to take this particular value over to the right side. Why, sir? Just for convenience sake, nothing special. Just for convenience sake, I am going to write this as first equation. I am going to write this as first equation. Okay, sir. What is the next thing you are going to do? The next thing I am going to do is, last time we studied how we are defining, in the last lecture we studied how we are defining angular momentum. What is angular momentum, or L? L is equal to mvr, which is equal to nh by 2 pi. Integer multiples of h by 2 pi. Angular momentum of Bohr's shells can be given as nh by 2 pi, integral multiples of h by 2 pi. I am going to square this particular term. If I am squaring it, what will I get? M squared. Okay, let me write the two slightly neatly. M square V square R square, which is equal to n square H square divided by 4 pi square. Okay, bring this particular value here. Can I write M square V square R square as mv square into mv square into mr square. Can I write m square v square r square as mv square into mr square? Yes, it can be written like this, equal to n square h square divided by 4 pi square. Here let me bring this particular mr square over here right hand side denominator to right hand side denominator. So I am going to write this as 4 pi square. Let me bring this to the bottom, which is mr square. So I am going to mark this as the second equation. Let us note the first equation and the second equation. Here we have two unknowns. What are the two unknowns? Radius of the nth orbital given by r and velocity of the electron given by v. Radius of the nth orbital given by r and the velocity of the electron given by v. So I have two equations and two unknowns. According to my 10th standard linear equation, if I have two equations and two unknowns, I must be able to solve the equation. So how am I going to solve the first equation and second equation? Kindly look at the LHS. Both have mv square. So I am simply going to equate the RHS. So the RHS must also be same. I am going to write 1 by 4 pi epsilon naught ZE square divided by R is equal to n square h square 4 pi square 1 divided by mr square. Okay sir, let us solve this. Can I cut 4 pi here and 4 pi here? Okay, can I cut r here and r here? Then let me continue writing this. ZE square whole divided by, here there is a 1 by epsilon naught, 1 by epsilon naught ZE square, that's it, there is no r over here. This can be written as n square h square divided by pi 1 divided by mr. Here what are you going to do sir? I am going to calculate r. So I am going to bring this r to over to the left hand side top. So r divided by epsilon naught is equal to what next sir? N square h square divided by pi into here there is only m. I am going to bring m over here. This ZE square, I am going to push it over to this bottom. 1 divided by ZE square. Are you getting this right? Okay sir. What next? Next I am going to bring this particular epsilon naught to over here to the top. R is equal to epsilon naught h square. I am going to bring n over here. Then what am I going to do? I am going to rearrange the denominator like this. Right? Why are you rearranging it like this sir? Notice this particular value, epsilon naught is permittivity of free space. Its value is given here. H is Planck's constant, value is given. Pi is 3.14, obviously. M is mass of the electron, E is charge of the electron. All these values are constants. So these constants can be substituted and this particular value can be calculated as 0.529 angstrom into n square by z into n square by z. This is the actual formula. This is the actual formula for radius of the nth orbital. Radius of the nth orbital. So these two formulas are very important. These two formulas are very important. Let me note these two formulas over here so that we can use them later in our problems. Can I note down these formulas? Are you comfortable with how I did my derivation? Okay, let me note it down. R is equal to epsilon naught h square divided by pi m E square into n square divided by z. Here this is a constant. This is a constant. Okay sir, what else? So this constant can be worked as here. Even though you are getting 0.529, it can also be approximated as 0.53 angstrom. Here obviously you are getting 0.529 angstrom approximately. This can be again approximated to 0.53 angstrom into n square by z. Sir, is there anything significant that I need to understand over here? Yes. There is a significant thing that you need to understand over here. What is that, sir? Kindly note the derivation, especially this particular last point here. The radius is directly proportional to n square and the radius is inversely proportional to z or atomic number. This particular relation can be used in a variety of problems. Are you able to understand this? So we found the value of the radius of the nth orbital. We calculated the constant. Sir, using this, draw a diagram and give us a practical illustration of what is happening. Okay, let us say here there is a positively charged nucleus. So I am going to draw, this has n equal to 1, n equal to 2, n equal to 3 and n equal to 4. These are 4 shells. These are 4 shells. Okay, sir, what is n? N is the quantum number. It simply represents the number of the shell from the nucleus. It simply represents the number of the shell from the nucleus. So I am going to write n equal to 1, n equal to 2, n equal to 3, n equal to 4. Okay, then I am going to write, this is going to be my ground state, this is going to be my first excited state, second excited state and third excited state. Fine, sir. Now here, how will you find the radius of each and every orbital? We will use this particular formula. We will use this particular formula. Can I use this formula within this box? Okay, sir. Use this formula within this box. Here, the entire calculation can be analyzed for hydrogen atom. We are going to analyze the entire thing with respect to the Bohr's orbitals in hydrogen atom. Okay, R here is equal to 0.53 angstrom into what is the value of n? N is simply n. We need to know the quantum number or the shell for which we are calculating the radius. But Z is the atomic number and for hydrogen it is simply 1. So the formula I am going to use here is 0.53 angstrom into n square. So here what is the value of n? The value of n is 1. I can simply write for n equal to 1, R is equal to 0.53 into 1 square. Here R is equal to 0.53 into 2 square. Why, sir? Because here n is equal to 2. Here, since this is the radius of the first orbital, I am going to put the value 1. This is the radius of the second orbital, I can put 2. What about the radius of the third orbital? 0.53 into 3 square, because n value is 3. What about the next one? R4 is equal to 0.53 into 4 square. Why? Because here n is equal to 4. Here all the radius values are measured in angstrom. All the radius values are simply measured in angstrom. Are you comfortable with this particular derivation? Sir, here what is the significant thing that you want to tell to us? I am going to write R4 over here. I am going to write R4 over here for a very specific reason. I want this space for working something out. Okay, sir. Here R4 is this particular value. I want to find the ratio of the radii of hydrogen. I want to find the ratio of the radii of hydrogen. It can be done. It is not a tough thing. In fact, let me give you an idea. 0.53 is called as Bohr's radius. The radius of the first shell of hydrogen. Kindly note down. It is a very important 1 mark, can also be asked as a 2 mark. Bohr's radius, the radius of the first shell of hydrogen atom that has been calculated by Bohr is called as Bohr's radius. It is nothing but R1 is equal to 0.53 angstrom. 0.53 angstrom. So here I am going to compare R1 is to R2 is to R3 is to R4. Let me write the values. Here, let us call this particular 0.53 as R0. I am going to call 0.53 as Bohr's radius. And what is Bohr's radius? Bohr's radius can be given as R0. Okay, so here what is my R1? R1 is simply R0 is to what is my R2? R0 into what is 2 square? It is 4. Okay, then the value is for the radius of the third shell, R0 into 3 square. The next thing, R0 into 4 square is 16. So here when I am simply comparing the values, I can cut off all my R0s. So the actual radius comparison is 1 is to 4 is to 9 is to 16 is to, obviously the next one is 25 is to, the next one is, I am simply going for 1 square, 2 square, 3 square, 4 square, 5 square, the next one is 6 square, the next one is for the 7, n equal to 7, it is 49, which is 7 square. Are you comfortable with how I am comparing the radius of the each and every orbital? Are you comfortable with the formula? Can we go for a couple of problems based on them? Okay, kindly note that these particular problems that I am going to work will deepen your concept, and not just that. These problems are in fact old board problems that are often repeated word by word. So I will sincerely recommend you guys to wait for these problems. Try these problems. So we have written those formulas over here. We can back refer from those formulas. Oh, this cloth is not rubbing very well. I am finding it very hard. Yeah, I am more or less at the end of getting a clean board for my problems. Yeah, cheers. Now I am going for the problems. Okay. Yeah. Thank you. And these are my problems. Yeah, let us go for these problems. Okay, let me rub this off. I did these tick marks when I was teaching in Tamil. Okay, let us go for the first problem. Find the radius of the third shell. Okay, find the radius of the third shell of the He plus particle. So what is the formula for radius? Radius formula is R is equal to 0.53 angstrom n square divided by z. They are asking for the radius of the third shell. Third shell means n is equal to 3 of He plus particle. He plus particle is obviously a single electron species, so it is not an issue. What is the next thing? N is equal to 3 for helium. Z atomic number is equal to 2. I am going to substitute these particular values over here. R is equal to 0.53. So what is n square? N square is 3 square divided by 2 angstrom. So this can be written as 0.53 9 by 2 angstrom. This is basically the radius value they are asking for. You can mathematically calculate this value. Am I right? Okay, let us go for the second problem. Okay, pause the video. The first problem and second problem are more or less similar with a very small twist. Pause the video, Tango. Pause the video. Try it out. Come on. You can do it. Have you tried it? Can I go for the problem? Once more. We are going to use the same formula. They are asking to find the radius of the fourth excited state. They are asking to find the radius of the fourth excited state of Li plus particle. Okay, the formula is R is equal to 0.53 angstrom n square divided by z. What is the value of n here? N is equal to, they are asking for fourth excited state. Okay, let me try it here. For n equal to 1, we have ground state. Okay, sir. For n equal to 2, you have excited state 1. For n equal to 3, you have excited state 2. For n equal to 4, you have excited state 3. They are asking for fourth excited state. For n equal to 5, you have excited state. Am I getting this right? 4. Yes. So for fourth excited state, what is the n value? N value is 5. For fourth excited state, n value is 5. So I am going to write a 5 over here. Yeah. Okay. Then they are asking to find for Li++ particle. Once more, it is a single electron species or hydrogen-like species. Such a kind of species where there is only one electron can be named as single electron species or hydrogen-like species. Okay, I am going to write here Zt equal to 3 because it's lithium. For lithium, atomic number Z is 3. Let us substitute. R is equal to 0.53 angstrom. Yeah, multiplied by 5 square divided by 3. 5 square divided by 3. So what is the R value? 0.53. 25 divided by 9 angstrom. 25 divided by 3. The square is only in the top. 25 divided by 3 angstrom. Are you comfortable with this particular idea? Yeah. Okay, Tangam. Let us go for the third problem. With respect to the third problem, what have they given? They have given that the radius of the innermost electron orbit of hydrogen atom is 5.3 into 10 to the power minus 11 meters. Okay, now let us do this. Here you have a positively charged nucleus. They are talking about the, give me 1 second, here this is n equal to 1, n equal to 2, n equal to 3, n equal to 4. The radius of the innermost electron orbit is 5.3 into 10 to the power minus 11. So the radius of n is, R1 is 5.3 into 10 to the power minus 11 meters. 5.3 into 10 to the power minus 11 meters. They are asking us to determine its radius in n equal to 4. They are asking us to determine the radius in n equal to 4. How are you supposed to find this particular value? In order to do this problem, we are going to use the proportionality idea. R is directly proportional to n square. Okay, so R is directly proportional to n square, which means R1 or the radius of the first orbital is directly proportional to 1 square because 1 is the quantum number or n value over in the first orbital. What about R4, which is the radius of the electron in the n equal to 4 shell. N equal to 4 shell. It is directly proportional to 4 square because that is the value of the quantum number in the n equal to 4 shell. In order to eliminate this particular proportionality constant, I am going to simply divide both the equations. So R1 divided by R4 is equal to 1 divided by 16. Yeah. Okay, I know the value of R1. R1 is 5.3 into 10 to the power minus 11 meters whole divided by R4, which is equal to 1 by 16. So R4 can be written as 5.3 into 10 to the power minus 11 meters multiplied by 16. This can be once more written as 5.3 into 16 multiplied by 10 to the power minus 11 meters. Are you comfortable with how I did the problem? While comparing the radius of two orbitals, you simply write the proportionality idea. You simply use the proportionality idea and divide the both of the equations. Divide both of the equations and get a relation. Use that relation to derive the answer. Use that relation to derive the answer. Okay, Kanna. What about the next problem? The fourth problem is something similar. Can you guys try it out? The fourth problem is something similar. Can you guys try it out? I will give you a couple of seconds. The fourth problem is something similar. Can you guys try it out? Okay, let me go for it. Yeah. What about the fourth problem, sir? What about the fourth problem? In the fourth problem, the orbital radius of the first excited state. Carefully note it down. They are not giving ground state. For ground state means you will write n equal to 1. First excited state means n equal to 2. So for first excited state, n is equal to 2. So I am going to write, yeah, give me 1 second. Let me draw this neat. So here n is equal to 2. For n equal to 2, first excited state, here n equal to 1, here n equal to 2, n equal to 3, n equal to 4. I can call this first excited state, second excited state, third. Okay, I am making couple of mistakes. Kindly bear with me. Ground state, first excited state, second excited state, third excited state. Okay, what have they given? They are asking for they are saying that the first excited state's radius is 2.1. The first excited state are n equal to 1, radius is 21.2 into 10 to the power minus 11 meters. Here R2 is equal to, what am I writing here? Here R2 is equal to 21.2 into 10 to the power minus 11 meters. So what is, they are asking for the radius of the second excited state. For the second excited state, n equal to 3. So they are asking for radius of R3. Let me compare the equations. R2 is directly, here R is directly proportional to n square obviously. R2 is proportional to 2 square. R3 is proportional to 3 square. If I divide both of them, R2 by R3 is equal to 2 square by 3 square. This can once more be solved as, 4 divided by 9. Let me substitute the values that I know. What is R2? R2, we know it as 21.2 into 10 to the power minus 11 meters. Whole divided by R3 is equal to 4 by 9. I need to find my R3, which is equal to 21.2 into 10 to the power minus 11. I will get a 9 over here, whole divided by 4 in meters. If you solve this, you will get the value they have asked over here. For radius of the second excited state or n equal to 3 state. Radius of the second excited state or n equal to 3 state. Are you able to understand this particular idea? Okay, sir. But you did tell us that you will derive the velocity of the electron. How are you going to derive the velocity of the electron in the nth orbital? Okay, we already studied in Bohr's postulates how angular momentum of each and every orbital is defined. Okay, let us do a recollection of this, of that particular idea. L is equal to mvr equal to nh by 2 pi. Let us consider this part alone. Here I am simply going to find this particular v value. V is equal to nh divided by 2 pi. I am going to bring mr over here. So here I can substitute the r value from this particular derivation. So nh divided by 2 pi 1 divided by m into, what is the r value? R value is epsilon naught h square divided by pi m e square n square divided by z. Yeah, are you comfortable with how I wrote this? Now how am I supposed to solve this particular equation? I will cut pi here and pi here. I will cut m here and m here. Then I will write nh divided by 2 within brackets 1 divided by epsilon naught h square n square completely divided by, okay, here it is e square. While substituting, I left a e square over here. So I am going to write e square into z. This can be written as, what am I going to do here? This particular part can be flipped above. So nh divided by 2 e square z epsilon naught h square n square. What else am I going to do? I am going to cut n and n. I am going to cut h and h. How can I write this particular equation? I can write this particular equation as, bring e square outside, e square by 2 epsilon naught h, e square by 2 epsilon naught h z by n. What is this? This is nothing but velocity of the electron. But e square is the charge of the electron, epsilon naught is permittivity of free space, h is Planck's constant. If I am going to substitute these values, this can be worked out as, I think you will get 2.19. 2.19 into 10 power 6 meters per second, which is in fact a constant, into z by n. Here the velocity, as we clearly noted down, the velocity is directly proportional to z. The velocity is inversely proportional to 1 by n. The velocity is directly proportional to z. The velocity is inversely proportional to 1 by n. Okay, sir. So how are you going to show a diagrammatic illustration of the change in velocity. Let me repeat, the diagrammatic illustration of the change in velocity of each and every orbital in what atom? In hydrogen atom. In hydrogen atom. Let me show it over here. Here the velocity of the first thing is, I am going to use this particular formula. I am going to use this particular formula. Here this is the velocity of the electron in the nth orbital. 2.19 into 10 power 6 meters per second into Z by N. For hydrogen, okay, let us do a demarcation here. V is equal to 2.19 into 10 power 6 into Z by N. But for hydrogen, what is my Z value? My Z value is 1, which is simply my atomic number. So, for each and every shell, what will change? N value alone will change. So V1 is equal to 2.19 into 10 power 6 divided by N value is 1. V2 is equal to 2.19 into 10 power 6 divided by 2. V3 is equal to 2.19 into 10 power 6 whole divided by 3. V4 is equal to 2.19 into 10 power 6 whole divided by 4. This is the progression in which the velocity value is slowly decreasing. This is the progression in which the velocity value is decreasing. Are you able to understand how to analyze this? Okay. Can we do one single problem? Can we do one single problem with respect to this particular formula? In fact, you can try it out. I will give it to you as a homework. Sir, what is the problem, sir? We will try that particular problem, sir. Find the velocity of the electron in the second excited state of He plus particle. Let us use this particular formula. Kindly check it out. The velocity of the electron in second excited state. Second excited state means what is N value? N value is 3. Check it out. For second excited state, N value is 3. For helium means, for helium, what is Z value? Z value is 2. If you are going to substitute these two values over here, you will simply get the velocity of the electron in the second excited state of He plus. In the second excited state of He plus. Aren't these problems very easy and simple? They are just comparing different quantities with respect to proportionalities. Right? Okay, in this particular derivation, we derived the radius of the electron in the nth orbit. We derived the velocity of the electron in the nth orbit. And we did some problems based on them. Hope you guys enjoyed this lecture. Yeah, this is a slightly long lecture. Hope I didn't bore you guys. Cheers and thank you for listening to me. Hope to see you guys in the next lecture. If you like our lectures, like our videos, subscribe to us, click the bell icon, recommend our channel to your friends, forward our channel using social media. Let us have fun learning physics together. Thank you, Tangam. Thank you.